morning everybody. Hope you're all healthy and safe at home. So we shall continue with our section 17.2, powers and roots of complex numbers. So in the previous lecture we had discussed about how we can express a complex number in the polar form, and with the help of that we were able to determine the power of a complex number z raised to n. So if you recall, the last thing that we had explained or considered or found out was that z raised to any integer power, that is z raised to n, where z is a complex number, is equal to r raised to n into cos n theta plus I sin n theta. Okay, that's what we had derived with the help of multiplication and all. So now we are going to use or learn a very important formula which is called as the De Moivre's formula, and it is related to the concept of the powers of complex number. That is, if the modulus of that complex number is 1, okay, that is if mod z is equal to 1, that is r is equal to 1, then we get cos theta plus I sin n theta whole raised to n will be nothing but 1 raised to n into cos n theta plus I sin theta, or cos n theta plus I sin n theta. So this is the important formula which we'll be using to do many problems and all. So if we are considering the complex number with modulus r equal to 1, modulus equal to 1, then z is equal to cos theta plus I sin n theta, I sin theta. So in that case z raised to n will be nothing but cos n theta plus I sin n theta. So that is an important formula, and with the help of this itself we will be able to find the corresponding roots of a polynomial. So let's move on to the roots of a complex number, not a polynomial, sorry, roots of a complex number. So we had studied in our lower classes that if you have a polynomial equation and all, we can find the roots of that particular polynomial equation, right? So in a similar manner, we can say that any number is said to be the nth root of a non-zero complex number if w raised to n is equal to z. Okay, any number is said to be an nth root of a non-zero complex number if w raised to n is z. Here w and z can be treated as complex numbers, so w raised to n equal to z means that w is the of the complex number z. Okay, and from that we can obtain this expression which is wk, which is equal to r raised to 1 by n into cos theta plus 2k pi by n plus I sin theta plus 2k pi by n. So let's just see how we can derive that particular expression. It is mentioned in your textbooks. It's not as such a proof of thing, it is just how we can find the equation that we have just now stated. So if you see, if you consider w to be the complex number rho into cos phi plus I sin phi, and z as r cos theta plus I sin theta, okay, these are the polar forms of the numbers w and z. Now w raised to n, what will be w raised to n by the expression? W is a complex number, so the power of that complex number would be nothing but rho raised to n into cos n phi plus I sin n phi. This is what we had discussed in the previous lecture, and this will be if w raised to n is equal to z. Suppose that w is a nth root, then w raised to n is equal to z, so we get rho raised to n into cos n phi plus I sin n phi will be equal to r cos theta plus I sin theta, right? So here we will compare the similar terms. So we can see that rho raised to n is nothing but r, that is rho is equal to r raised to 1 by n, right? And what will be cos n phi plus I sin n phi will be equal to cos theta plus I sin theta. Now again, comparing two complex numbers, we will equate. If two complex numbers are equal, their real parts should be equal, and correspondingly their imaginary parts should also be equal. So in this case, cos n phi must be equal to cos theta, and sin n phi must be equal to sin theta. So from this we can get that n phi will be nothing but theta plus 2k pi, because after a period of 2 pi cos and sin values gets on repeated. So cos n phi is equal to cos theta implies n phi is equal to theta plus 2k pi. Okay, where k is any integer. 2 pi, 4 pi, 3 pi, all these will give the corresponding values. So n phi is equal to theta plus 2k pi. So from this, what will be the value of phi? Phi will be nothing but theta plus 2k pi by n. So what have we got? We have obtained that if w is written as rho into cos phi plus I sin phi, we obtain rho is nothing but r raised to 1 by n. So we'll replace it there, and we replace phi by, or you can replace it by theta plus 2k pi by n. Okay, so let's just see what was the formula that we had seen. We had seen that w is equal to r raised to 1 by n cos theta plus 2k pi by n plus I sin theta plus 2k pi by n, right? So here you can see that the nth root, we know if we are asked to find the cube root or the fourth root of unity and all. So in fourth root of a particular complex number, so in those cases we know what the value of n is. So if you see in this expression, we will be knowing what is r, and we'll be knowing what is n. So the only term that this w depends upon is k. So we give the notation wk. So the root can be determined of the nth root of a complex number can be determined by substituting different values for k. And here we have to note one more thing, that is the value of k will definitely be varying from 0 to n minus 1. Okay, because once k takes the value 0, 1, 2, 3, etc. n minus 1, we'll have n distinct roots. Okay, after that, when the value of k is greater than equal to n, what happens is, since the function sine and cosine is 2 pi periodic, which I had mentioned earlier, the values will get repeated. That is, suppose that the proof is given in your textbook. That is, suppose that k takes the value n plus m, where n is 0, 1, 2, 3, etc. That is, k takes the value n plus 1, n plus 2, etc. Any value greater than or equal to n. What happens? Let us substitute the value of k as n plus m. It will become theta plus 2n plus m pi divided by n, right? So that is theta plus 2n pi plus 2m pi. Now n and n gets cancelled. So what will we get? We can replace this as, or this is equal to theta plus 2m pi by n plus 2 pi. Okay, phi is nothing but theta plus 2m pi by n plus 2 pi when k is some value greater than equal to n. So what will be sine phi? Sine phi will be sine of 2 pi plus some angle. So sine of 2 pi plus theta is sine theta itself. Okay, so using that identity and using the concept that sine and cosine are 2 pi periodic, we will get, for any values of k greater than equal to n plus m, we get greater than equal to n, we get sine phi is same as sine theta plus 2m pi by n. So actually, to find the nth roots of the non-zero complex number, there will be basically n distinct roots, and the formula is, which we had mentioned in the slide, that is for any complex number z is equal to r cos theta plus I sin theta. The n distinct roots, nth roots, are given by wk is equal to r raised to 1 by n into cos theta plus 2k pi by n plus I sin theta plus 2k pi by n, where k is varying from 0, 1, 2, 3, etc. n minus 1. Now there is one more thing that I have to mention, that is the principal nth root of a complex number. That will be the value when k is 0. Okay, so that we can see after doing an example. So example 4, we are asked to find the 3 cube roots of z. Actually there will be only 3 distinct ones. So we are asked to find cube roots of z is equal to I. So we are given the complex number. Now with the help of that, we are going to determine what is r and theta, right? R is equal to nothing but the modulus. So modulus, or if you see the polar form, here r is 1, and theta will be argument of z. That will be nothing but tan inverse of y by x, whatever it is, that will be. And we know that we have done in the previous lectures and all, argument of I, the complex number I is nothing but pi by 2. So what will be the polar form? That will be, it will be z will be r is 1, so z is equal to cos pi by 2 plus I sin pi by 2. Okay, so now we can find, once we know the polar form of the given complex number, given any complex number, we can easily convert that into the polar form. So once we know the polar form, we can apply the equation that we have determined just now. So for n is equal to 3, what will happen? Wk will be nothing but r is 1, so 1 raised to 1 by 3 into cos theta, here it is pi by 2 plus 2k pi by 3, n is 3, plus sin pi by 2 plus 2k pi by 3, where k varies from 0, 1 and 2. N is 3, so n minus 1 is 2. Okay, so we'll get 3 cube roots of z equal to I. So now we can determine what are the values. When k is 0, w0 will be nothing but 1 raised to 1 by 3 is always 1. So cos pi by 2 by 3, that is pi by 6 plus I sin pi by 6. So that is nothing but root 3 by 2 plus 1 by 2i. And when k is 1, we will get w1, which will be equal to cos of pi by 2 plus 2 pi, that is 5 pi by 2 divided by 3, that is 5 pi by 6. So cos 5 pi by 6 plus I sin 5 pi by 6, that will be equal to minus root 3 by 2 plus 1 by 2i. And finally k equal to 2, w2 will be equal to cos, when k is 2, we'll get it is 3 pi by 2 plus I sin 3 pi by 2, and that value will be nothing but minus I. So these are the 3 roots of the complex number z is equal to I. So here when k is equal to 0, we call it as the nth root of the complex number, principal nth root of the complex number. So in this example, if you view the numbers or the roots that we have obtained are very good numbers, that is they lie in the circle and on the boundary of the circle, and they are equally spaced. Okay, you can see figure 17.2.3 that the roots of this particular complex number, they are lying equally spaced, and they are behaving in a very good manner. But this is not necessary for all the complex numbers. So that you can see in the next example which is given, we are asked find 4 fourth roots of unity. So here n is equal to 4. Don't get confused with this 4 fourth roots of unity. Nth roots of, to determine nth roots of unity, we are using the formula. Okay, and nth roots of unity we will always obtain n number of distinct roots. Okay, so that's why 4 fourth roots of unity. So here n is equal to 4. So and the complex number is z is equal to 1 plus I. So here x is 1 and y is 1. So we can see what is r will be root of 1 square plus 1 square, that is root 2, and theta will be the argument of z, that is tan inverse of y by x, that is tan inverse of 1, that is pi by 4. So we can apply the equation and we get wk will be equal to root 2 raised to 1 by 4 cos pi by 4 plus 2k pi by 4 plus I sin pi by 4 plus 2k pi by 4, where k varies from 0, 1, 2 and 3. So when we substitute the values, we'll get the following values, which is given, that is when k is 0, we'll get w dot, then the value is 1.0696 plus 0.2127 I, and correspondingly the values you can determine when k is 1, 2 and 3. So you can see that these numbers are pretty much we cannot easily plot in the circle, and they need not be equally spaced and all. So that is not true in every case, it's just that it happens in some of the few numbers. So that's what I had to discuss in this section, and that is the end of this section also. That is basically the concept of roots of any complex number. So in this section basically we have determined how we can write a complex number in its polar form, then how we could find the power of a complex number, that is z raised to n is equal to r raised to n into cos n theta plus I sin n theta, and with the help of that we found the De Moivre's formula, and also we found or we determined the nth root of a complex number, and there will be n distinct nth roots of a complex number. So the formula is wk is equal to r raised to 1 by n cos theta plus 2k pi by n plus I sin theta plus 2k pi by n, and it varies for the value, it depends upon the value of k varies from 0 1 2 3 etc n minus 1. So that's it. With this we shall wind up today's session. Thank you. Stay home and stay safe.